All right, ladies and gentlemen, welcome back to my YouTube channel. Thanks for tuning in. Today's a very special day.
Through the computer.
Today's a very special day because we get to learn about logarithms today.
That was so enthusiastic.
We should have had
Are you drawing a log?
He's a teacher.
That logarithm.
That's a log. It's a log.
It's a frog. There needs to be a leaf.
The Kermit the Frog sitting on log.
Who's got
Walking.
legs? Who's got legs? Wow.
Oh.
He's running.
Logarithm.
That's a.
Oh, cause
Who's tapping the
I didn't know that you were good.
Logarithm.
Oh.
Wow.
I love it. Yes.
Where's the little stick with the leaf?
Do you want us to draw that in our notes?
Yeah, would you? Okay, so put that in your notes. Go ahead and redraw that in your notes.
I will.
All right. Yeah. Plug that in your calculator. Hit that button. Find that image on your calculator. Hit that button.
There you go.
All right.
It's not in the map.
I have a question for you. How many times could you double $1 to get to $8?
I can.
Three times. Right? You double it once. How much money do you have? Twice? 3 times? $8. Right?
Oh, gosh,
You
yeah.
could double it 3 times to get to $8. Okay? Now, we could use an exponential equation to model this situation, right? 2 to the x would be equal to 8. Do we all agree with that? My starting value is 1. Remember these equations that we had the other day? Little a times 1 plus or minus r to the t. Basically, the starting value is what's sitting out in front of the base. So if my starting value is $1, so I want to double it each time. Notice how my base of my exponent is now 2 if I'm doubling it each time. I want to know what the exponent would be if I could get it up to $8. Right? That's how we model this situation. 1 times 2 to the x is equal to 8. And obviously, I think we can all reason through that we would plug in 3 for x. Right? 3 would get me up to 8. We may be able to solve this equation by using mental math if we know that 2 to the 3rd power is equal to 8. So you would have to double $1 3 times to get to $8. That's a pretty simple example, right? Okay. However, what about 512? You should keep plugging in random numbers, right? I mean, we could figure this out.
4.
Is it 9?
I think so.
You think so? Because he just did 2 to the something equal, 2 to the 5th, 2 to the 6th, 2 to the 7th, 2 to the 8th, 2 to the 9th power, right? We could logically reason this through again, but there's an easier way, there's a simpler way, there's a more mathematical way to solve these things. It is 9. To solve that equation, 2 to the x is equal to 512. Like right now, before today, if I was given this 2 to the x is equal to 512, we don't know how to solve this equation. How do we get x out of the exponent? We don't know yet. So what must be the inverse operation of taking an exponent? That's okay. They can hear me still. What's the inverse operation of taking an exponent? Well, it's a logarithm. Okay, so there's our formal definition of a logarithm. A logarithm is the exponent to which a specified base is raised to obtain a given value. Okay, that's our formal definition of a logarithm. A logarithm is an exponent. Okay, so that's an interesting starting phrase there. The logarithm is the exponent. It's equal to the exponent. The logarithm is equal to the exponent. So which a specified base. So now we're saying the base is actually very important. A logarithm is equal to the exponent to which a specified base is raised to obtain a given value. That's really what a logarithm is. It's always equal to the base. Logarithm is equal to a base. logarithm is equal to the exponent to which a specified base is raised. I have the general form down there. Oh no, it's on the next page. I see it right there. Okay, anybody still need that screen? Okay. So I would definitely write down this conversion. This is the conversion from exponential form into logarithmic form. Going from exponential form into logarithmic form. So if I've got b to the x is equal to a, I know that's going to be log base b of a is equal to x, and that's how we would read that. Now, this is assuming our base is greater than 0, and also not 1, right? We talked about that when we introduced exponential functions. As long as the base is non-zero and positive, and not 1. Again, negative bases make it non-real. Weird things happen. So that's why it can't be negative. Okay, so now take a look at your conversion. Now, honestly, a lot of today is just figuring out what these logarithm things are and doing like building block basic stuff with these things. So one of the things that we're going to talk about is how do you convert? If a logarithm is truly equal to an exponent, how do we convert an exponential equation into a logarithmic equation? And this is the conversion. Okay, so if I've got like b to the x is equal to a, let's actually figure out something that we could write with this. Like, okay, 2 to the third is equal to 8, right? We know that 2 to the third is equal to 8, correct? To convert that into logarithmic form, what we do is we take log base 2, log base 2, and the 2 is written as a subscript of the word log. Log shorthand for logarithm. Log base 2 of 8. Log base 2 of 8. Okay, and by the end of like section, I don't know, like 7.5 or something, I'm going to be able to give you log base 2 of 8, and you will know 3. You will be able to perform that operation in your head. Like what I'm saying here, if I was not given 2 to the third is equal to 8, if I asked you what this was equal to, what you're looking for is what base or what power do I raise 2 to get 8? That's what I'm really asking you here. What is the exponent on 2 to get 8? 3. Log base 2 of 8 is equal to 3. It's equal to the exponent. Okay. One of my students proposed this to me, I don't know, 7 or 8 years back. They said, Mr. Albert, I think of this as whenever I transfer from logarithmic into exponential and exponential to logarithmic, I think of it like a spiral. Because you start here, log base b of 8 is equal to x. That's the way they think about it. Log base b of a is equal to x. Also going back, I could transfer these arrows going forward and backward, because these statements are equivalent. You could say b to the x is equal to a. However you want to think about it is fine. Just know the conversion. So let's do a couple more of these. Let's just think about some powers. Let's go 3 squared is equal to 9. 3 squared is equal to 9. A true statement that we know. 3 squared is equal to 9. Perfect. Okay. 3 squared is equal to 9. That would turn into, oops, I'm sorry. That's exponential form. Turning that into logarithmic form, that would be log base 3 of 9 is equal to 2. You see that? Log base 3 of 9 is equal to 2. The base of the log is always equal to the base of the exponent. The base of the log, what gets written below the log, is always equal to the base of the exponent. Okay. What's another power that we could do? What's like I don't know. Let's do just 3 to the 5th power. What is 3 to the 5th power? 243? Oh yeah, because that would be 81 times 3. So 3 to the 5th is 243. That's a true statement that we know. We can say log base 3 of 243 is equal to 5. What's 8 to the 4th power? Somebody do that for me. Whatever 64 times 64 is. 4096.
The number.
Okay, so 4096. That would mean log base 8 of 4096. See, the bigger you make your base, like the smaller your number is going to be when you have an exponent, or when it's equal to over here, right? Because it's only going to take a smaller exponent to get really big. Think about how base of 8 grows really, really quickly, right? I only need a 4 over here to get all the way up to 4096. Right? Base 8 is going to grow a lot quicker than like base 3 or base 2. All right. Yeah, below. Okay, yeah, we talked about that. All right, so let's do some examples. Why don't you guys try to transfer those for? Take them from exponential into logarithmic. All I'm asking you to do is just switch it up. Take it from exponential and put it into logarithmic. Okay, I'm just going to write these up here. So this is going to be, did we just do 3 to the 5th?
Yeah.
Aw, bummer. Log base 3 of 243 is equal to 5. Log base 25 of 5 is equal to 1/2. That's interesting. And then we've got log base 6 of 1/6 is equal to -1. And then we've got log base A of C is equal to B. How do we do? Feel all right with that? Okay. Flip it. Do the other way around now. Again, gotta crawl before we can walk. Just perform take it from logarithmic into exponential now. Got to learn the language a little bit. Okay, so now we've got 9 to the 1st power is equal to 9. 8 to the 1/3 is equal to 2. We'll actually talk about fractional exponents this chapter. That's fun. Hashtag foreshadowing. 4 to the -2nd power is equal to 1/16. B to the 0 is equal to 1. How'd we do? We do all right? Good. Yes, there will be questions like that on the next test, on the next quiz. Just straight up transfer from one to the other. Just got to learn and process through what does it mean, and try to think about it logically. Never put an answer on the blank that you don't trust logically. Like if you screwed up letter A here, and you accidentally wrote like 9 to the 9th is equal to 1. I mean, think about what you're doing there, right? That's not correct. Okay. All right. One thing that I wanted to point out. Everybody look at D there. That's a special property. If I didn't know what this was, and I asked you b to the what power, b to the what power always gives us 1. Taking anything to the what power always gets you 1. 0, right? Taking anything to the first power, you always get itself back out again, right? Which is the other special property that we'll talk about on the next slide. Taking anything to the 0 power always gets you 1. Now, I know 0 to the 0 is a little weird, but haven't we excluded 0 as a base? So taking 0, b to the 0 is always going to equal 1. Take a look here. Oh, this is b to the b. That's the one that I was talking about. The first one is the one that Thomas set up. B to the b. How do you make something always stay the same? You raise it to the first power. So if you ever have log base b of b, and b could be anything, as long as it fits our restrictions, b could be anything. Log base 1,000 of 1,000, 1. Log base 7 of 7, 1. Log base x of x, 1. Log base pi of pi, 1. As long as it is the same number, base as the of number, log base b of b, it's always going to be 1. Why is that true? Because I'm thinking about keeping it the same. What power do I raise it to keep it the same? The first power. And we've already talked about the log of 1 property. The log of 1 property, that's the one that says that, how do I make everything just turn into 1? Raise it to the 0 power. So that's what it's equal to. It's equal to the exponent, so it's equal to 0. Whenever you have log base b of 1, it's always 0. That is equivalent to 0. So log base 10 of 1, 0. Log base 7 of 1, 0. Log base x of 1, 0. Log base pi of 1, 0. Log base e of 1. Ooh. What is e? We'll talk about e this chapter too. Oh, yes. There's so many fun things. Whoa. Okay, now, there are certain, and it's actually interesting that I bring up e at this point, there are certain logarithms that come up a lot, like log base 10. Log base 10 is called common log. Log base 10 is called common log. Guys, if you look on your graphing calculators, can you find the log button? Hit that log button. Does it give you the option of putting in a new base? Does it give you an option of changing the base? What's written down below the log? Anything? No. There's nothing written down there. Guys, just like if I had like x plus 4. What's the power on x if there's nothing written there? You assume that it's just a 1, right? X to the first power. If it's a logarithm, and there's nothing written as the base, you assume it is a common log. Common log is base 10. So looking at your calculators, your log button is base 10. Your log button is base 10. That's common log. We will learn a little bit more later about, do you see right below the log button, the LN button? That is what's called a natural log. Natural log, that's log base E. So your calculator has two buttons right on the front of it that perform logarithms. Log base 10 and log base E. Now, your calculators, you can change the base. You just have to hit math to go in and change the base. I would show you that on my screen, but guess what? My calculator doesn't have that ability. Your calculators just started having that ability, like within the past 2 years. These new CE editions. Check yours. Can you hit math? Can you change? Is there a logarithm button in there? No, his.
You get a special one.
Oh, nice.
Scroll down. Where is it? Is it just right there? On the first? Yeah, see, this calculator cannot change base. That's how recent this update is for these calculators. You won't need to use that very often. You may use it to check your answers and stuff, but because you've gotten that ability now, we have to give this test in 2 different sections. A calculator and then a graphing calculator, a red calculator and then a graphing calculator. So because your calculators have gotten a little bit more advanced, we have to restrict your use a little bit. Don't throw your calculator, Swope. Be nice. So your calculators do common logarithm, which is log base 10, and it will also do natural logarithm, which we'll learn about a little bit later on. Okay, so let's try to think without writing anything down. Let's try to figure these out without transferring the form. Now, if you need to fall back on to transfer the form, totally fine, like on your homework and stuff tonight. But do I even need to change the form? Can I figure this out mentally? Remember what this is saying. 5 to the what power is 125? Well, think about it logically. What's 5 squared? 25. Well, then what would 5 to the third power be? 25 times 5, right? Is that 125?
Yeah.
I've got 5 quarters. Do I have $1.25? Yeah. So I know that this is equivalent to, remember it's always equal to the exponent, 3. Okay, so what would that be? -1. Why do you say -1? Exactly. Whenever you have a fraction, it's going to be a negative exponent, right? He's thinking this, right? That I just transferred the form. I turned this into exponential, right? I went like this and changed the form. 5 to the what power is 1/5? He's thinking, okay, if it turns it into a fraction, it's got to be a negative exponent. It's got to be. So that means this should just be, and if it keeps it the same, it's just got to be -1. Just got to flip it, make it the reciprocal. That's weird.
Whoa.
So
Because log nothing.
Yeah. So log of what? Right? Okay, so 10 to the what power gives us this? -5th power, right? 1, 2, 3, 4, 5. Right? 10 to the -5th power. That would be a -5. Okay? That make sense? Now, on your homework tonight, it's going to say like, oh, perform it using mental math, but you have a calculator. You can fall back on if you need to. Now, because logarithms are the inverses of exponents, the inverse of an exponential function such as y is equal to 2 to the x is a logarithmic function, such as y is equal to log base 2 of x. Guys, think about this. We just got done with this section of inverses, and we know how to find an inverse now. If I know my function is f of x is equal to 2 to the x, now I can say to you, find the inverse of that. Well, how do we do that? Well, the first thing that we do is change f of x is equal to y, and then what do I do to find the inverse? Just like I did here, I switch x and y, and then what do? I resolve for y. How do I solve for an exponent? By taking a logarithm. So all I need to do is just change this from exponential form into logarithmic form. Log base 2 of x is equal to y, and now it's resolved. So these two things are inverses of one another. Right? So what does that tell us graphically about 2 to the x and log base 2 of x? What did we learn yesterday about the graphs of these two things? It's reflected over the line y equals x. It's reflected over that diagonal line. So, what does that mean? Well, that means a lot. Take a look at the graph. So let's analyze. There's a lot of stuff that we could talk about in here. First thing, the domains and the ranges are switched, aren't they? The domains, because we took an inverse, right? X's became y's and y's became x's. What was the original domain of an exponential? It was all real numbers. So what's the range of the logarithm? All real numbers. You see that, how the x's and y's switch? If the domain of the exponential was all real numbers, the range of the logarithmic is now all real numbers. What was the range of the exponential? It was greater than 0, right? So what's the domain of the logarithmic? X is greater than 0. Do we see that? The domain is x is greater than 0. The range is all real numbers for the logarithmic, because it flipped from the exponential. The domain of the exponential was all real numbers, and the range was y is greater than 0. So now transferring it into logarithmic, it flips because it's the inverse. The domain is now x is greater than 0, and the range is all real numbers. The asymptote is also the inverse, right? Think about, where was the asymptote in an exponential? At y equals 0, right? So what's the inverse of that? X equals 0. It is no longer a horizontal asymptote, but it is a vertical asymptote. Okay? So everything changes. Everything is the inverse. So the asymptote was here for my exponential, right? It was always getting closer and closer to 0. The y values were going to get closer and closer to 0. Now the x values are going to get closer and closer to 0. Okay? I believe that was all on that side. Okay, perfect. Let's graph one. I guess, whatever. Let the cat out of the bag a little bit there. Okay, so we're going to graph this. Now, this is just exponential, right? I could have given this graph to you when did we start learning exponential? Last Friday, right? So if I go to graph this, 1.25 to the x, I put in -2, I get 0.64. Let's put in -1. 1.25 to the -1. That gives us 0.8. To the 0 would be 1. To the first power would be 1.25. And 1.25 to the second power gives us 1.56. Okay. Let's do to the third power. 1.95. Man, it doesn't grow very fast, does it? Whatever. Okay. Now, what would the inverse of that function be? What would the inverse of this function be? Give me the equation. What would f inverse of x be equal to? Log base 1.25. Of x. Okay? Now, I don't need to do any new calculations. Why not? Because they're right here. What do I need to do with my x's and y's? Flip them, right? So, for the sake, look at that. Oh my gosh, I'm so good. Look at that. They're all there already. That's smartboard magic right there. Smartboard magic, nothing up my sleeves. All right, so we got -2, 0.6 something. We've got -1, 0.8, 0, 1, 1, 1.25, 2, 1.56, 3, 1.95. See, it's going to grow, but it's just going to grow at a really slow rate there. Okay. A couple things that I would check. Again, make sure your y-intercept is in your right spot. Make sure it should not cross the asymptote. Right? And now I'm going to graph my red. 0.64, -2. Well, I guess 0.64, a little bit further. 0.8, -1, 1, 0, 1.25, 1, 1.56, 2, sure, 1.95, 3. Oh, somewhere over here. Okay. Don't cross. Man, it shouldn't have curved back around, but you know what I mean. So the red line is the logarithmic, the blue line is the exponential. Did I need to do any new calculations? No, right? Because in your calculators, not all of you can calculate log base 1.25. So I can't give you something where I'm going to force you into calculating log base 1.25. I'll show you how to change the base. I'll let you do that eventually, but okay. The last new thing, again, the book always likes to give one word problem on how logarithms do real world application, and this is just one of them. It's a chemistry application. You ever wonder how they calculate pH? No, not really. Like it's just, you know, the paper turns red or blue or something, right? So it's actually determined by the hydrogen ion concentration. Okay, the hydrogen ion concentration in moles per liter. Okay, here's what this means mathematically. Okay, because the higher the concentration, the bigger it grows exponentially. Okay, so if I want to flip that around and find the pH given the hydrogen ion concentration, what's going to happen is it's going to turn into a logarithm. What type of logarithm? What base logarithm? A common log, log base 10. Okay, so that means to find the pH of milk, if I had somehow done an experiment and found the hydrogen ion concentration is all of that, I would take the negative log of 0.1, 2, 3, 4, 5, 6. 1, 2, 3, 4, 5, 6. 2, 3, 4, 5, 6. 2, 5. Right? If I wanted to find the pH of tomatoes, negative log of 0.0000316, and lemon juice, negative log of 0.0063. Okay, let's do that real quick. What do we expect for milk? High number or low number? What do we expect from lemon juice? Low, right? Isn't acid low?
Yeah, like 6.
Negative log 1, 2, 3, 4, 5, 6.
This is basic.
Come on, guys,
Can I die?
this is basic. Actually, isn't 7 like middle of the road?
Yeah.
So milk is like middle of the road.
Whoa.
Negative log of 0.0000316. I think I've put one, not too many zeros. And then negative log of,
That's
Okay.
extremely.
so those are my pHs. So if you ever wonder how do you calculate pH, you can use a logarithm.
I'm so glad I know
How
that.
cool, right? All right, YouTube world, see you. So long, farewell.